Okay, so let's have a little look at deductive reasoning. Now we've already, just by way of review, we've already talked just a little bit about a conditional statement. What's a conditional statement?
If this happens, then.
It's an if-then statement. Good. So an if-then statement. If, what do we call the if part of the statement? Good. And the then part? Conclusion. Okay. So how would we, what does it mean? Like, let's take the example, if it is sunny, then we will play soccer. Okay? So the if then. Somebody state for me the converse of that statement. If it is sunny, then we will play soccer. The converse. What's the converse going to be? Jesse? Yeah, we just flip it backwards, right? If we play soccer, then it is sunny. Whether or not it's true, that's the converse, right? Okay, what is the inverse? The inverse of that. What do you think? Yes, ma'am?
If it's not sunny, then we won't.
Yeah, okay, so we're going to negate it, right? Negate both parts. If it's not sunny, then we won't play soccer. And the contrapositive. Cassie, remember what the contrapositive is? Okay, the contrapositive is kind of a weird one, Duncan.
If you don't play soccer, then it isn't sunny.
Right, okay, so you're doing both. You're negating it and you're flipping it around. So it's a combination of the converse and the inverse, right? Okay, we also talked just briefly about what happens if we have a statement that works in both directions. Like, for example, I think we had the example we used in class was if you are a brunette, then you have brown hair.
Yeah.
Is that it? Okay. So that's true. What's the converse of that statement? Okay, if you are a brunette, then you have brown hair. What did I say first? Well, we get the idea. One of them is if you have brown hair, then you're a brunette. The converse would then be if you're a brunette, then you have brown hair. Is that true?
Yeah.
Yeah, they're both true. So if both the conditional statement and its converse are true, how can we join those? By conditional statement. Right, and there's very short homework I want to add. I just wrote some more. It'll take you no time at all. It's a biconditional statement, and the biconditional statement just tells us that it goes either way. Either the hypothesis or the conclusion. We could flip it around in either direction and they both work, right? We could interchange the hypothesis and the conclusion. That's a better way of saying it. What's our wording for that? How do we correctly state a biconditional statement? Yes, sir.
Something happens if only if this.
Okay, right. So in this case, we would say, if you have brown hair, if and only if you are a brunette, and that's equally as good as you are a brunette if and only if you have brown hair. It's the if and only if is what indicates that it's a biconditional statement, that it goes in both directions, right? Okay. All right. So today we're just gonna build on that very slightly. So deductive reasoning, we want to be able to do today, we're just going to add a couple of small things. This is kind of important. We want to add some symbolic notation that represents all the stuff that we've talked about. And then we're going to just apply 2 rules of logic, real simple rules of logic, but I think it's good to actually see, this will be good for you. So symbolically, if we have the statement, if the sun is out, then the weather is good. Okay, so which is the hypothesis? Sun is out, conclusion, the weather is good. Okay, so let's just symbolize the statement by saying P is going to be our hypothesis. So P represents the statement, the sun is out. Q represents the conclusion, which is the statement, the weather is good. So symbolically, we can say all that stuff like this, right there. That's it. Oops, I think I lost my pen. I don't know why this happens, but sometimes it happens. Okay, there we go. All right, so we can represent all of this by that simple statement there. Okay, that's our mathematical way of saying P leads to Q, or in other words, if P, then Q, okay? The converse, how would we write it? Well, we're just gonna interchange the Q and the P, because remember what they stand for. The P stands for the hypothesis and the Q stands for the conclusion, right? So this is the converse of our original statement, okay? You just interchange the P and the Q. Does that make sense? P and the Q could be anything. In this case, we put some specifics in there for P and Q, but in general, this is the converse of if P, then Q, okay? All right, so, Alex, put that away. Put away, thank you. Okay, so what about this? What if we want to say both of them at the same time, like we were just talking about? What if we have a statement that is true in both directions? We can say if P, then Q, or we could also say if Q, then P. That was our biconditional statement, or if and only if statement, right? Well, here's how we write that. We just have a two-way arrow. Makes sense, doesn't it? Because now we can either start at P and go to Q or vice versa. So we read this as P, if and only if Q. Symbolically, that's how we say it. Right? So try this. So on your notebook paper, just scratch this down for me. So let's let P be the statement, the value of x is -5, and let's let Q be the statement, the absolute value of x is 5. So first, write this statement. I'm not even going to read it. Just part A, I want you to write that statement in words. And maybe you can just say it. If you think you don't even need to write it, that's fine. Okay, Maisie, how do we do A?
If the value of x is -5, then the absolute value of x is 5.
Good. Okay, just a regular conditional statement, if P then Q. How are we going to do part B? First of all, what is part B? What is part B? Kirk, what would you call that? If this is our conditional, what's that going to be?
Converse.
Converse, good. Okay, how would you say it?
If absolute value of x is 5, then the value of x is negative.
Okay, so now if we're going to make a valid biconditional statement, both of those have to be true. So we have to decide whether the biconditional statement is valid, whether it's true. Okay, what do you think? Matthew, Demi, what do you think?
Yes.
Okay, so let's take it one at a time. So would you agree, yes or no, true or false, if P then Q works?
Yeah.
Okay, true. Anybody dispute that? So we're saying if the value of x is -5, then the absolute value of x is 5. Anybody think of a counterexample? I can't. That one, I'll buy it. That one's true. Okay, what about the converse? Converse is if the absolute value of x is 5, then the value of x is -5. Now you're shaking your head false. Okay, so you've got, give me a counterexample that proves it false.
That proves this false?
Yeah, that proves this false. Right? That proves this statement false.
If.
Okay, well now let's think about what that's going to mean. If we have to come up with a counterexample, let me write this statement real quick. I'll just write it quickly. So if Q then P says if the absolute value of x is 5, I'll just write it using math, right? Then x equals -5. It's kind of our shortcut math way of saying that, right? Okay, so Daphne, you think we have to be able to come up with a counterexample. If this is indeed false, we have to come up with a counterexample to demonstrate that it's false. How many counterexamples do we need?
One.
Just one. That's all it takes.
If the absolute value of x is 5, value of x is also 5.
Okay, good. Perfect. Because when we come up with a counterexample, remember that the structure of a counterexample is very specific. P still, or whatever the hypothesis is, still has to be true, right? We have to say that if if this is true, then come up with some different counterexample, and the counterexample is x is 5, right? X could be 5. That make sense? Okay, so that's false. So we can't write it this way, can we? Okay, make sense? Questions on that? Okay. Okay, and here's what we came up with, right? The conditional statement in part A was true, but the converse in part B was false. Okay, writing negations. So far we know how to write a converse now. That's no big deal. We just flip the P and the Q. But how do we do when we deal with inverses and contrapositives? We have to be able to have negations included, right? So our symbol for negation is just this tilde. So then, for example, if these are our statements, if P is the statement, that's what that's saying. This statement P is angle 3 measures 90 degrees. Statement Q is angle 3 is not acute. Okay? What's the negation of P going to be then? If angle 3 measures 90 degrees, there it is, right. Angle 3 does not measure 90 degrees, is the negation, right? Because the negation has to include everything except that statement, right? Okay, now this is a little trickier. What's the negation of Q? Angle 3 is acute. Exactly. Did everybody see that? So now that's kind of tricky. Think about this. If the original statement Q is angle 3 is not acute, think what it means to say, I would just essentially be saying angle 3 is not acute. What does it mean to say something is not acute? It is acute, right? Because a not cancels a not. Kind of like in the very same way that a negative cancels a negative, right? Make sense? So an easier way to think about that is the negation of a not is just the absence of that not. Okay, everybody see that? So angle 3 is acute would be our negation of Q. What's another way of saying that? Not Q. Okay. So we said the other day that a conditional statement is equivalent to its contrapositive. Remember what the other two, it tells us. The other two that were equivalent were the converse and the inverse of the original conditional statement, right? Okay. They skipped something here. I want to, before we jump into this, can anybody tell me that if this is our original conditional statement, we already said that the converse is if Q then P. What's the inverse going to be? How am I going to write it symbolically? Okay, everybody see this, the squiggly, called a tilde, right? So we're going to say tilde P leads to tilde Q. So if not P, then not Q. Yes? Say it again.
It's tilde.
Oh, tilde. Oh, I am. Okay. Oh, okay. That's my whole life I've called it a tilde.
Because you pronounce it wrong.
Oh, okay. Well. Oh, okay. All right. Tilde. Okay. Thank you. It's good to know. So that's an inverse. Now, what's a contrapositive going to look like then? Is okay. Tilde Q. Good. So the way we'd say that then is if not Q, then not P. Okay, and remember that the ones that are equivalent are those two say the same thing, and these two say the same thing. Yes, sir. Mathematics has so many symbols because we want to be as compact and precise as we can.
Mr. Robertson said it was because they were lazy.
Sort of, and partly because, I mean, that's probably part of it. But honestly, I'll tell you what, that is a legitimate reason too. I'll just give you a little personal anecdote. I can remember doing by far the hardest math classes I took in college were my physics math classes. Way harder than my theoretical math classes. I had a quantum mechanics problem set once with 3 problems on it. It was a week-long problem set, and it took me almost 200 pages of just pure math, symbolic math to get it done. So it would have been like 1,000 pages if I hadn't had the opportunity to like use symbols. That was a brutal one. That was like, I still have nightmares about that one. That wasn't normal. But the thing is, when you get to college, there are some cases where, the math gets dense. It's just pages and pages of symbols. And there's no way you'd get like carpal tunnel syndrome trying to write out an assignment like that or do a problem like that if you couldn't use these nice compact symbols. And so there really is something to that. It's kind of like you're being lazy a little bit, but you're also saying, okay, I got to be able to write this and read this without getting confused. And so that's a real reason though, too. It really is. And the other part is the symbols help us be very clear in what we're saying. And the example I've sometimes used with people is, remember the game Telephone you played in grade school? And it's a great way, like I guarantee, and we'll try this sometime, but for now I'll just tell you what, and we'll verify it. But if we play Telephone and we give some message up here that's like like something you would want to tell your friend, or something that's like an English sentence that includes some information. It's amazing, and you've all seen this, I'm sure, how contorted that gets by the time it gets to the other end of the room. Because you kind of have the ability with, if I want to say John is going to be waiting for you after class with an important message, then you guys could say, okay, well that's, when I pass that on, I might slightly change that because now I've internalized the meaning, but there's a bunch of different ways you can say that using words, right? And so it's natural for people maybe to just kind of change the direct sentence, but in their mind the meaning is the same. Now you can't do that with math though, right? If we're starting with the statement x squared plus 3 equals 7, well, there's really no way to internalize that, and that's the message, right? X squared plus 3 equals 7. It's going to get passed on the whole time with no changes because there's no reason to change it. It's perfectly clear and you can't make it any better, right? And so that's the other reason we use symbols, is because of the game of telephone. No, because we want to make things clear and concise and unambiguous, okay? All right. So if a conditional statement then is if P then Q, so let's say P is the statement, the car will start, and Q is the statement, the battery is charged, right? So if the car will start, then the battery is charged. The contrapositive it says the same thing, they're equivalent statements. So what would the contrapositive be? If not Q, then not P, right? What's that gonna look like? If the battery is not charged, then the car will not start. Aren't those the same statements? Aren't they really? Aren't I saying the same thing? If the car will start, then the battery is charged. Isn't that the very same thing as saying, if the battery is not charged, then the car will not start, right? They include the same information, right? So they are equivalent statements, okay? Questions on that? Does that make sense? Okay, what about this one? What's the converse of that statement going to be? Now remember what the original statement was if the battery is... Right. The car will start. So if the car will start, the battery is charged. That was the original statement, right? What's the converse then? If the battery is charged, right, because that was originally our conclusion, then the car will start. Okay, that's the converse. What's the inverse going to be? Well, the inverse is going to be the opposite of what our original hypothesis would be. So not P. If not P, then not Q. If the car will not start, then the battery is not charged. If you think about those two statements, they're the same thing. They're completely equivalent. Right? Okay. So deductive reasoning then, what we're moving towards, in just a low level, but this is our first foray into deductive reasoning, where we're just going to use facts, definitions, accepted properties, in a logical sequence, so we can go from saying, if this is true, then this must be true, okay? Inductive reasoning is relying on patterns and observation, okay? So here's an example of inductive reasoning. Andrea knows that Robin is a sophomore and Todd is a junior. All of the other juniors that Andrea knows are older than Robin. Therefore, Andrea reasons inductively that Todd is older than Robin based on her past observations. Could she be wrong?
Yeah.
Yeah. Is that a complete list of all the students? I mean, not necessarily, right? But it was a quick way to come to a conclusion. Is she probably right?
Yes.
Probably, right? So inductive reasoning is quick, maybe not perfect, but it's quick, okay, in this sense. Okay, now deductive reasoning. Andrea knows that Todd is older than Chan. She also knows that Chan is older than Robin. Okay, so could she then, does this make sense, that Andrea reasons deductively that Todd has to be older than Robin based on those statements?
Yeah.
Okay, yeah, it is. That's what we're going to come to call the law of symbolism, or syllogism. Okay? Syllogism. This is, so the law of detachment just says this. If P then Q is true, if that's a true conditional statement, and if that's true and P is true, then Q has to be true. Okay? Think what that said. Now say that again. If the logical statement, if P then Q is true, okay, and P is a true statement, then Q has to be a true statement, right? Does that make sense? Okay, what if P then Q is a true conditional statement, but it turns out that P on its own is false? Then Q is not necessarily true, is it? Right? Yeah.
You go back to the definition
The definition of, say it again.
of deductive reasoning.
Oh, sure, yeah. Deductive reasoning, well, I can tell you what it is. Deductive reasoning is just, the definition really as it's written down is not that big a deal. Deductive reasoning is just is using logic to show that something is true. Whereas inductive reasoning is just following a pattern to assume something is true. Okay? For example, if two angles form a linear pair, then they are supplementary, right? So we could then say angle A and angle B are supplementary, so they form a linear pair, right? What about two separate angles whose sums happen to add up to 180 degrees but aren't adjacent? See what I'm saying? Are they a linear pair? No, they're not, right? Okay, so we can find examples where, yeah, this statement is true. If A, then B is a true statement. But maybe A is not true, right? If two angles form a linear pair, well, what if they're not a linear pair, right? Then you can't say necessarily that they're supplementary, right? Does that make sense? Okay, and then how much time do we have, like 2 minutes?
Yeah.
3 minutes? Okay, this is the last one. We're about done. So here's the law of syllogism. This one is really simple. This one just says, if P then Q is true, and the statement, if Q then R is also true, what conclusion could you make, do you think? Well, if P then Q is a true statement, and if Q then R is a true statement, could you connect P and R?
Yeah.
You could, couldn't you? You could say, if P then R also must be true, right? For example, if a bird is the fastest bird on land, then it is the largest of all birds. If a bird is the largest of all birds, then it is an ostrich. Okay, those are both true statements. So then could we say correctly that if a bird is the largest of all birds, that if a bird is the fastest bird on land, then it's an ostrich? Yeah, we can. We absolutely can, right? That's true. Okay, make sense?
Yeah.
All right, I think we better call our quits. Oh, here is your
We have a teensy bit of math.
teensy bit, not much.
And there's one online too.
Yeah, it's very short. This is very short. One page, one side of one page. I'll put these available online as PDF so you can print it out and use this or something.
Is it due tomorrow yet?
No, I'll put this will be for Wednesday.
Alright. There you go.
What time is this class over at?
Who's gone? Anybody gone today? Look around.
Yeah, this person.
Oh, okay. Who else? Anybody else gone?
He's not, he's off the class.
Yes.
I just have to take the test.
Oh, that's fine. Yeah, no problem. I get you for TA. We can do it.
That'd be good.
Want me to do that for tomorrow?
Could I do it Wednesday?
Sure.
So
That's
I'm
fine.
gonna study for a test.
Okay, that's fine. Just remind me tomorrow, and I'll get you for Wednesday. Okay.
Can I have one question left on it that I need to finish on my test.
Okay, you can do it. We can TA after school, whatever works best.
Can I do it during TA tomorrow?
Yep,
Okay.
that works. Yep. That makes sense? That makes sense today? Okay, good.
Thank you.
Uh-huh. Yes, you are.
Hello.
Hello.
What did we do Friday in here?
Friday, we started a lab.
Oh, that's right.
Started a lab.
You watch the game on Saturday?
I did. It was,
They almost beat us.
they did. They did. They played really well. That's a tough place to play. It's a really tough place to
It
play.
was rated the entire game.
It looked miserable. I mean, it looked just, and the rain looked like it was just coming down sideways. It just looked horrible.
Yeah.
You guys had fun though?
It was a lot of fun.
Yeah, good.
Who did they play?
Stanford. It came down to the last second, literally. Missed field goal.
That's fun.
Yeah,
I
that's,
couldn't tell. They missed it by much.
he missed it by a fair amount.
They kept it pretty good.
Yeah.
I could tell why he kicked out. Like, oh no.
That's, I mean, that was pretty tough conditions to kick under.
So he was 5 for 5.
And he's 5 for 5 going into that, I know. And he'd hit one that was a decent, I mean, a fairly long field goal too.
You gotta go 6 for 6 in a rainy day.
Yeah, no, it is. Absolutely. Man, that quarterback, he's a tough son of a gun. He got hit hard. I mean, he'd get up and I didn't think he was going to get up. What's that? Yeah, yeah. Yeah, they shut.
I just love it. It keeps me
What?
I can go see you. You can go, Thursday, and then I'm heading back to Friday afternoon.
Okay. Sure.
So this is one of the book assignment questions. Not sure which equations to use.
On 29. Which one was that?
Yeah, it was 29, and it gives you the final velocity, like the time period it takes over, and the displacement, but it doesn't give you the acceleration, and it asks for the initial velocity.
Okay. But it implies that he's accelerates constantly to a velocity of 7.5. So what's that implying about his starting velocity?
Zero.
Yeah. Yeah. So that's going to help.
Okay, so do I find the acceleration?
Yeah, you can do it that way. You don't have to. That's one way to do it.
Wait, but it's asking for the velocity.
For V naught, yeah. For the original velocity, zero. Right. Yeah. Yeah, that's one way to do it. You could solve for A, or you could just do an average velocity too. Just find displacement by average velocity times time. Okay. Okay, so we got a short day today. Here's my thought. Okay, my thought was rather than try to get into the lab on a short day and get going, we'll pick that up tomorrow. Let's go ahead and go through the 5.2 and the 5.3 part 1 assignments. So I stapled these and I didn't mean to. That was kind of dumb. No, we did 5.1 we've gone through, but we haven't gone through these yet.
Yeah, I don't want to go. I'm going to try to convince Nicole to say, hey, we'll run it.
Yes.
I promise I did it, but it's sitting in
Well, that's fine.
on my bed.
That's fine. That's fine. Just go through it as best you can with us. But that's fine. Just bring it next time. I'll give credit for it.
Yes. I'm not upset. Yes. Well, maybe. I hope I am, but I just feel like I know Keegan. She's our lowest. Or our highest.
Yeah. We're gonna go through these. These are solutions. We're gonna go through the assignments and talk about these a little bit. You might see that.
Oh no, no. I should have paper with that.
Okay, so here's the deal. Listen, please. So on these, consider these to be sort of a warm-up for. I'm going to give you a Moodle problem set here the next day or two that I think is just a little bit better. It's one where I feel like the problems will all be different, so that's the one that'll be maybe worth it. This is just going to be worth it. Not much. But
So we
consider it a
just
warm-up.
shouldn't do it.
No, do it. Definitely do it. But I want to go through it and talk about and see if there's any questions that come up. We kind of want to just address, once again, how do we approach kinematics problems like this? Maybe we can go through a couple on the board if we need to. et cetera, et cetera. Tomorrow we will jump back into finishing up, maybe not, hopefully we'll get close to finishing up the lab, but you can be working on lab/rest of 5.3. Make sense? And then we'll go through the other 5.3 assignments, hopefully, maybe let's say Wednesday. I think Wednesday is the official date, so we'll go through those on Wednesday. We're going over the 5.2 one, which is not up there, but I'll tell you what the numbers were. And then the first 5.3 one. Okay? So you're going to want to have your book or be next to somebody that has a book.
Oh wait, shoot.
So partner up with somebody that does then.
Where are all your books, sir?
I've got some books. There's one. Here's some down here.
Can I have it?
Yes, you can.
Yeah.
There's
Not
book.
forever, but-
Book.
Me too.
Okay. There's a book.
Also, I have something I need to tell you. Okay, so I'm gonna be gone Wednesday, Thursday, and Friday.
Okay.
What do you want me to do about the lab?
You'll just have to finish up the back, I guess.
Okay, so am I just gonna like copy one of my partner's like note, like packet thing, or what do you want me to do?
Let me think about it. We'll see. We'll see how much. Maybe part of it, and then part of it I'll have to do.
Said we only have one.
We'll figure something out. Okay, we ready? I did. Probably should clean my desk, huh? Okay, here we go. Here we go. So, 2.6. The first part of 2.6 was, I think it was just 13 through 16. That's all it was on page 93. So let's look at those. No, we didn't go over it though. Yeah, we didn't go over it. So this is the one where we started dealing with velocity time graphs. And I think most people are going to be probably okay with this, but I want to make sure that we're okay. So use figure 510. So figure 510 is the one that's actually on the solutions, right? Okay. That is a velocity time graph. And they want to know, determine the velocity of the airplane that is speeding up at 1 second. Well, I mean, what am I doing there? On the graph, where would I find that? Do I need to get a slope? No. It's a velocity time graph, right? So it's giving me the velocity on the vertical axis versus time on the horizontal axis. So I'm just going to go over to t equals 1 and see what the y component of the graph is at that point. It looks like it's what? 74. Yeah, so the answer is, at 1 second, the velocity is 74 meters per second, right? So at 2 seconds, it is what? 78. At 2.5 seconds, it looks like it is 80. Okay, questions on that? Just reading the graph, that's it. Okay, the factor label method, I do not like the way they did this. Let's quickly go through it our way instead. Our way is better.
You recording this?
Oh, should I record this?
No.
Would you like, anybody like, raise your hand if you'd like me to record this. Anybody? Okay, I'm gonna record it then, absolutely. Oh, I think I've been recording.